Hello APChem, this is Mr. Coker, and this is our third and final lesson of Chapter 16, and I think if you check it out, it's actually our last equilibrium lesson. We're going to be looking at complex ions. Complex ions are when metal ions get surrounded by molecules or ions, kind of like we see here with the 6 waters forming a hydration sphere around copper plus 2. Or besides water, something like ammonia can also do this, and so ammonia can form a complex with copper. Here's one where ammonia and water are working together to form a complex on the right. These have interesting colors. You see that copper plus 2, when it's surrounded by waters, makes a light blue color. Copper with 4 ammonias and 2 waters makes a royal blue color. Mainly what we're interested in here is that complexing metal ions with things like water and ammonia can change its solubility. So let's get our definitions down. A complex ion is a charged species consisting of a metal ion surrounded by ligands. The ligands are these waters or ammonias or whatever that surround the metal ion. We say that they are a Lewis base. They're an electron pair donor. That's another definition for acid and base. Electron pair donor, Lewis base, electron pair acceptor, Lewis acid. But mainly what we're interested in here is it needs to be a molecule or an ion that has an electron pair that it can donate to an empty orbital on the metal ion. The metal ion, of course, has a lot of empty orbitals on it because it's lost its valence electrons or many of its valence electrons. So these molecules or ions like water or ammonia can use their unshared pairs to form covalent bonds with these metal ions. It's called a coordinate covalent bond. So some common ligands are water, ammonia, as we saw previously. Chloride can be a ligand. Cyanide can be a ligand, just anything with an unshared pair of electrons. Now the number of ligands surrounding the metal ion is called the coordination number. These are typically 4 in maybe a tetrahedral arrangement or 6 in some kind of octahedral arrangement. And examples of these complex ions might be a cobalt plus 2 with 6 waters surrounding it, or a copper plus 2 with 4 ammonia surrounding it, or maybe a silver plus 1 with 2 ammonia surrounding it. So you can have different coordination numbers, and you can have different ligands surrounding these ions. Like I said earlier, these often have some really pretty colors, but our main focus in this unit is going to be that the metal ions using these ligands will have an equilibrium, and it can affect the solubility. Equilibrium constants for these ligands to surround these ions, the equilibrium constants for those reactions go by a couple of names. They're sometimes called formation constants, or they're sometimes called stability constants. Now they're often quite large, and this large size is important because what this allows to happen is it allows these ions, which typically form from dissolving of a relatively insoluble ionic compound, allows those ions to be bound, and basically that removes them from the right side of the equation, and that shifts the equilibrium to more solubility. So since they form these complex ions with pretty large equilibrium constants, you can assume that these ions are pretty well bound up in water to make these coordination compounds. In fact, the silver reacting with 1 ammonia has a K of 2.1 times 10 to the third, and then reacting with the second ammonia has a K of 8.2 times 10 to the third. So we put the two reactions together and add them together. Silver reacting with 2 ammonias to make the double complexed silver ammonia complex would have a K something like 1.6 times 10 to the 7th. I believe the math would be. Remember, if you add reactions, you multiply the Ks. So in solution, you're going to have a little bit of silver ion, you're going to have some ammonia molecules, you're going to have some silvers with 1 ammonia complexed on it, and some silvers with 2 ammonias complexed on it. And these 4 things are all going to be in equilibrium with each other, with the 2 ammonias attached to a silver looking like the one below. So let's take a look at this silver ammonia reaction. Let's say we mix 100 milliliters with 2 molar ammonia and 100 milliliters or 100 milliliters of 2 molar ammonia with 100 milliliters of 1 times 10 minus third molar silver nitrate. So to start with, we're going to have some silver ions, some nitrates, some ammonia molecules, and some water all mixed together. Now let's first consider what might happen between the ammonia and the water. Ammonia and water has a weak base equilibrium, an ionization equation, where it forms ammonium plus hydroxide. That would have a Kb of 1.8 times 10 minus fifth. Now that's a pretty small K, so this reaction is not real important. It's pretty minimal. Most of the ammonia is going to be NH3. Now we look at the initial concentrations. Because 100 milliliters is added to 100 milliliters, both volumes have been doubled and both molarities are cut in half. So the silver ion is not 1 times 10 minus 3, it's 5.0 times 10 minus 4 molar due to dilution, and the ammonia is not 2 molar, it's 1 molar due to dilution. So those are our initial concentrations of silver plus ammonia before the complexing coordination compound forms. Now, since the two Ks, K1 and K2, are large, I'm going to assume that all the silver ion first reacts with two ammonias to make the double complexed silver ammonium complex. I see a misprint here. There should be a 2 right here. Silver plus 2 ammonias make silver ammonium 2. Now the silver ion is a limiting reactant because it's quite small molarity compared to ammonia. So I'm going to assume that all of this molarity, 5 times 10 minus 4 molar, gets turned into silver ammonia 2. So after reacting, the silver ammonia taken twice plus 1 is going to be 5 times 10 minus 4 molar, the molarity of the silver ion before the reaction. Now the ammonia, I'm going to say it's still about 1 molar. Yes, a little bit of it reacted, but not enough to really budge us off of this 1 molar number. Now, we start with those two numbers, and we then look at the two equilibria. Starting with the second, we're going to work our way backwards from the second equilibrium. So using our K2 value, we can find the silver ammonia with 1 ammonia on it from the K2. So let's go back and think about what that K2 is. K2 is 8.2 times 10 to the third, and it's equal to the silver ammonia with 2 ammonias on it divided by the ammonia's molarity and the silver ammonia with 1 ammonia on it at equilibrium. So if we do a little algebra on that, we can solve for the silver ammonia with 1 ammonia on it by dividing the silver ammonia with 2 on it by the ammonia and the K2. Draw it out for yourself if you don't agree. So K2, silver ammonia, single ammonia, is 5 times 10 minus 4, the silver ammonia with 2 ammonias on it, divided by 8.2 times 10 to the, another misprint here, it should be 8.2 times 10 to the positive third, divided by 8.2 times 10 to the third, and also divided by 1 molar, the molarity of the ammonia. Now if you do that algebra, you get K2 equal to 6.1 times 10 to the minus 8. So that's a pretty small molarity. So that proves that most of our silver is bound up with 2 ammonias, not 1. Now, going back to K1, we can do that same kind of algebra with K1, where we solve for now how much of the silver doesn't have any ammonia on it. And that's going to be the amount of silver with 1 ammonia, 6.1 times 10 to the 8 minus 8, divided by 2.1 times 10 to the third. I think I did it again. I think I put a negative third on it when it should be positive third. So that's another misprint. Sorry about that. 2.1 times 10 to the third, and also divided by 1 molar. What? I'm going to let you watch me go back and fix both of these things that I've done wrong here so you can see what it should actually look like. Fix it right now. That should be a 2. That should be a positive 3, and that should be a positive 3. Now, let's go back to the presentation. Now everything is fixed on the slide. I'll get this little box out of the bottom. Okay, there we go. 6.1 times 10 minus 8 divided by 2.1 times 10 to the third, and also divided by the 1 molar for ammonia. So we get, using K1, that the silver ion is 2.9 times 10 minus 11 molar. So to summarize, we've got our silver ion, 2.9 times 10 minus 11 molar. We've got the silver single complexed with ammonia, 6.1 times 10 minus 8. We've got the silver double complexed with ammonia, 5 times 10 minus 4. We have the ammonia, 1 molar. So those would be the concentrations of everything. Okay, so for more practice, we're going to just go through and do another example of this. We're going to do silver plus 1, silver complexed with this thiosulfate ion, S2O3 minus, or AgS2O3 minus 2 actually. So when you put the silver plus 1 with the thiosulfate, you get a minus 1 ion, complex ion. And then we have the di-complexed thiosulfate. So we get the silver with 2 thiosulfates, which will have a minus 3 charge. So we're going to look at the concentrations of all 3 of those in solution if we mix 150 milliliters of 1 times 10 minus 3rd molar silver nitrate with 200 milliliters of 5 molar sodium thiosulfate. The stepwise formation equilibria are going to be the silver plus 1 plus the thiosulfate ion is going to make the single complexed silver thiosulfate there, which has a K1 of 7.4 times 10 to the 8th, really big. And then we have the single complex silver thiosulfate plus 1 more thiosulfate would complex to make the double complexed thiosulfate on silver plus 1 with a minus 3 charge, K2 3.9 times 10 to the 4th. Once again, pretty large. So let's start out with our initial concentrations. Now, because of the dilution, we're going to have to factor in what the addition of the 2 solutions to each other does to the molarity. So we're going to take M1B1 divided by V2 to get M2. So for silver ion, that works out to 4.29 times 10 minus 4 molar. And for the thiosulfate ion, that works out to 2.86 molar. So I think with those 2 large Ks, we can assume that virtually all of the silver ion is going to react to completion with the thiosulfate to make the double complexed silver double thiosulfate, minus 3. So at equilibrium, that's going to take on the molarity of the original silver ion, and it's going to now be 4.29 times 10 minus 4 molar. The thiosulfate has changed virtually none at all, so it's going to be 2.86 molar. So now we're silver thiosulfate single ion. We're going to find its molarity using K2. So we're going to take K2 and we're going to solve it for silver single thiosulfate. And we're going to get 3.8 times 10 minus 9 molar. And then we're going to use that to go in and solve for the silver ion in the first equilibrium using K1, and we get silver ion plus 1, 1.8 times 10 minus 18 molar. So to summarize here, silver plus 1 is 1.8 times 10 minus 18 molar, virtually none of it in there. Single complex, 3.8 times 10 minus 9 molar, still virtually none. Most of our solution is going to be thiosulfate that hasn't been able to complex with silver ion, 2.86 molar, and double complexed silver double thiosulfate there, 4.29 times 10 minus 4. Okay, so that's how you do the math on these. You do them a little bit like precipitation. You run them all the way to the right, then you go back to the left to do the equilibrium values for the different ions and complex ions. Now let's take a look at how this could apply to maybe qualitative analysis. In the previous section, when we were looking at qualitative analysis, we said that the group 1 metal cations, silver +1, lead +2, and mercury 1, which is actually a kind of diatomic mercury 1, Hg2 + 2. It's actually Hg +1, but it always comes in pairs. So these three ions in water can all be precipitated by adding chloride ion in the form of HCl. So when you add HCl to a mixture of metal ions to try to separate things out, you will get separated out silver chloride, lead 2 chloride, and mercury 1 chloride. However, what are you going to do with that mixed up precipitate of those three different compounds? Well, you can't adjust the pH and have any effect because chloride's not basic. So unlike what you can do with sulfide, where you can make it more acidic or less acidic and get different ones to dissolve or precipitate, doesn't work with these because chloride's not basic, doesn't react with H+. So you've got this mixture of these three metals. What might you do to begin to separate them out? Well, typically what you do with that precipitate after you've drained off the rest of the solution, the supernatant, is you add to that precipitate a large amount of concentrated ammonia. Now the ammonia is going to form a complex ion with the silver ion, which is going to then pull that ion into solution. Now you might be thinking, wait a minute, I thought the silver ion was a precipitate. Yes, it's mostly precipitate, but with any solid in water, there's a small degree, even if it's a small KSP, there's a small amount of silver ion that is going to be in equilibrium with that silver chloride solid. If you form a complex ion with it, that's the same as removing a product by turning it into something else. And now that's going to shift the equilibrium to the right, which is going to make more silver chloride dissolve. So you can actually dissolve the silver chloride out of this precipitate of lead 2 chloride and mercury 1 chloride by using this ammonia molecule to make a complex ion. Now just to prove that, let me show you the difference between the KSP of silver chloride without ammonia and then the K for dissolving silver chloride in ammonia. Now the KSP for silver chloride is 1.6 times 10^-10, but then if you single complex it with ammonia, that's K is 2.1 times 10^3, and if you double complex it, the second formation constant is 8.2 times 10^3. If we add all three of these reactions together, we get the reaction between silver chloride and two ammonias, making the double complexed ammonia ion plus chloride, and you get a K of 2.8 times 10^3. Now you may be looking at saying, well, that's still small, but it is quite a bit larger than the K without any ammonia. It's about 7 orders of magnitude or 7 powers of 10 larger. So then you might think, okay, that's still pretty small, so what do we do? Well, we might keep in mind we've got a really high concentration of ammonia. So think about the equilibrium. If you've got a large amount of reactant, that's going to shift the equilibrium to the right. So the reality is that even with this K being 10^-3, with a large molarity of ammonia, you can actually get quite a bit of silver ion to dissolve out of the silver chloride and make the diammonia complex. The qualitative analysis group 1 separation scheme might then look like something like this. You start with a solution that contains silver ion, mercury 1, and lead 2. You add some cold HCl, and that's going to precipitate the silver chloride, the mercury 1 chloride, and the lead 2 chloride. But now you've got this mixture of precipitates. What are you going to do? Well, the first thing you might use is a little bit of heat. It turns out that just warming the test tube a little bit, actually what you would do is you would decant off the liquid, then you would add distilled water back in, then you would warm that a little bit, and it turns out that lead 2 chloride is actually fairly soluble in warm water. So that would actually dissolve the lead plus 2 as we go to the left side of this flow chart. So we're here, we add some water back into the precipitate after we've drained off the supernatant. We add some water back in, we add a little heat, and our lead chloride dissolves. The silver chloride's not real soluble in warm temperatures, neither is the mercury one, but the lead chloride actually redissolves by just heating it. So now your solution is going to contain the lead plus 2, and your precipitate's going to still be the silver chloride and the mercury 1 chloride. Now if you drain off the precipitate, decant it, or draw it off with a pipette, you can add to that warm lead plus 2 some chromate, which will precipitate as lead 2 chromate, which is a yellow color. So now you've got a positive test for lead plus 2. Meanwhile, back over here, you've got your precipitate of silver chloride and mercury 1 chloride. By adding ammonia, you get the silver to go back into solution. And then you can drain off that supernatant. You can add a little bit of H plus to it. The H plus will turn the ammonia into ammonium, which will then let the silver bond with the chloride, because ammonium will not have the complexing ability that ammonia does. So the silver will go back into solution as Ag+. It'll find the chlorides and re-precipitate as silver chloride. So now you've got your precipitate of lead, which is yellow, and your precipitate of silver chloride, which is white. Remember, this was the supernatant from the adding the ammonia. So this is the liquid that you drained off into a separate test tube. You've added the H plus to it to neutralize the ammonia, and now you've turned it back into silver chloride. A white precipitate in this step would tell you you did have silver in the mixture. Now, the ammonia that you added actually also has a reaction with the mercury 1 chloride. What it does is it performs a reaction with that, which turns it into liquid mercury, which will have like a black color. And then this molecule here, Hg and H2Cl, which is white. So your precipitate is going to look gray because it's going to be a precipitate of the liquid mercury mixed with the solid Hg and H2Cl. So a gray precipitate after adding ammonia and dissolving out the silver is indication that you do have some mercury plus 1 as well. Okay, so here's some homeworks to try. The last of the review questions would be 8 through 10, and they talk about complex ions and different ways of using them to help dissolve stuff. Questions 20 to 22. We've done all of the active learning questions, I believe. And then the final exercises would be the odds from 65 to 80. So just like before, just like you to at least look at those questions. Think about whether you can do them or not. If you're not sure, maybe try them. Particularly try the blue ones because their answers are in the back of the book and you can check your work. Now, after you get to number 80, if you're feeling brave and you really want to delve deep into this topic, you might try some of the numbers, the blue ones between 81 and 121. Those are some higher level problems, some challenge problems, some problems that kind of use some topics maybe we've learned before, but those are ones that are pretty high level, and you're welcome to try those. But now's the time to start thinking about the multiple choice review questions, 1 through 16, because we finished up the notes. So now it's time to do the multiple choice questions. Email me a copy of your answers, and then I can give you some feedback on your answers for those 16 questions before you take the quiz. I'm going to post the quiz as a PDF on Friday, and like you to go through and answer those and send those to me, and I'll go through and correct that and let you know which ones you got right and which ones you got wrong. Don't forget, this week nothing counts. We're still working towards trying to get ready for the AP test, and I'll be getting back to you more with details about how we're going to review for that. But I'd like you to try the review questions, AP multiple choice review questions, and the quiz to make sure that you're up to speed on this topic of solubility equilibria. if there's any of the homework problems that you look at, you try, and you can't work, feel free to contact me. Let me know what those are. I might even make a little video of working those out to show you how they can be done, so you can look at how those are done on a YouTube video. Well, that finishes up for Chapter 16. So I'd like to encourage you to do the review questions, multiple choice review questions, and the quiz that I'm going to be sending out on Google Classroom. And then we can begin to think about how we're going to wrap up the year, because it looks like this may be the last of the new material that's going to be posted on the AP test. Don't forget, today there's a lesson being posted on the AP website. They're going to have somebody teaching a lesson. I'm not sure what it's going to look like, but that would be at 9 to 9:45 today. There's going to be a lesson posted on the AP website, and I believe it's an introduction to acid-base chemistry. Well, everybody stay safe and shelter in place as we all are. And while you're sheltering in place, use your extra time to work on AP chemistry, kind of like I've been with making these PowerPoints. Thank you very much.